So I'm going to be presenting on the basically the theoretical underpinnings of DFT. I wrote this presentation kind of in my based on what I wanted to learn about DFT. I wanted to know what made it work and why it was even developed as a quantum mechanical method. So in line with that, I will preface just by saying I'm not a complete expert on DFT, so I reserve the right to say I don't know to questions that you may present to me. But I tried to, so I made there are equations in here, but I do explain them with words, and the exact understanding of the math is less important than understanding what the equations mean. And so we're going to try and keep it fairly general. And then I want to also just briefly state that this talk is based on molecular ground state density functional theory. So like plane wave density functional theory for periodic systems or TD-DFT for excited states is not gone over in this talk. But you can look that up after this talk if you want. All right, so the talk will basically follow this general outline. We're first going to motivate density as the main variable in a quantum mechanics setting. And then we're going to go over the basic theorems that motivate DFT as being possible and useful, the Hohenberg-Kohn theorems. Then we'll go over the actual practical version of DFT that's implemented in most quantum QM packages today. And then finally, we'll talk briefly about different functionals that you can choose and the hierarchy of them, which in DFT is called Jacob's ladder. All right, so I just want to briefly review the main quantity that people are interested in quantum mechanics is the energy of a particular system, right? We use the energy to make potential energy surfaces, see what barriers are, calculate equilibrium, all that stuff. So the main way we do this is that we solve the Schrödinger equation, and before DFT, we basically just solved it by solving for this wave function and then computing the energy. Okay, I can just do it, yeah. So you see we can just get an expression for the energy in terms of the wave function. So this expression is termed a functional. It's a function of a function, and so that's where the functional comes from in density functional theory. And it's indicated throughout this talk by brackets. Most of the equations are functionals, so you don't really have to worry too much about noticing when I use a bracket or not. So people were fine using wave functions for a while, and then they started doing more and more expensive configuration interaction calculations. And at this point, they realized that the wave function is actually quite complicated, and that when you have a really long expansion of your wave function, it becomes hard to interpret what certain determinants, presences, mean. Also, the wave function is I just said it's complicated in the sense that it can be expanded in many determinants, but it's also complicated in that for a particular system of n electrons, the wave function is a function of 4 n variables. For each electron, you need to indicate spatial coordinates, x, y, z, as well as spin. So the larger your system gets, the more complicated your wave function can become. And some QM people just were not happy with the state of things. They thought to themselves that there should be a simpler function that the energy would be a functional of. And that's what motivated the line of inquiry for DFT. So the main idea of DFT is instead of considering the wave function, you consider the electron density. In the presentation, it's denoted rho. The electron density only depends on 4 variables, x, y, z, and spin, because you're not dealing with discrete electrons. And so, it would be nice if we could use the density, but it's still unanswered whether there is an expression for the energy in terms of the function or the density. That is energy a functional of the density? So in answering this question, it's essentially equivalent to asking if the Hamiltonian can be determined strictly by the electron density, since the Hamiltonian defines the wave function, defines the energy. All right. So, I just said we just need to see if the density defines the Hamiltonian. So we're going to take a look at the Hamiltonian. In particular, we're looking at the Born-Oppenheimer Hamiltonian. You'll notice, so again, form is not incredibly important here. You'll notice it's composed of three different terms. The first, so T is a kinetic energy. So first term is kinetic energy. Second is electron-electron repulsion. And third is the nuclear potential. So if you look at this equation, it may not be obvious to you, but from system to system, that is between different molecules, the form of these operators for kinetic energy and VEE don't change. So they'll be the same for any system you choose. What does change is the nuclear potential, in particular, the position of the nuclei and the nuclear charge. So to define the Hamiltonian, we really only need to be able to define the number of electrons as well as the nuclear positions and charges. Well, I accidentally hit the other arrow, but the Hamiltonian depends, so N can obviously be obtained just by integrating the density over all space, assuming you're given a density. All right, and then so what remains is determining the nuclear potential. Quick note, in DFT theory, they often call it the external potential, but external and nuclear potential mean the same thing in this talk. All right, so I've just put up the nuclear potential again. These are the two variables that we're interested in. And so I just put up a cartoon of a diatomic electron density. And just like Cody mentioned, there are cusps. And so it's kind of obvious that from the location of the cusps, you can probably get the location of the nuclei. Right? What is not so obvious is that you can also obtain the nuclear charge. This required some nifty thinking by some people. So this is called Cato's cusp. It turns out that how fast you decay from the cusp, how fast your density falls off from the cusp actually defines your nuclear charge. So this is, if you want to make sense of this, it's just a derivative at the cusp times some constant depending on the density. All right. So the external potential and thus the Hamiltonian are fully defined by the density, in particular by the shape and location of the cusps in the density. All right. So at this point, it would be naive of you, but correct of you to think that we've defined the Hamiltonian fully by the density, so we should have an energy functional. We should have an expression, but we're still missing one property, which is very key to actually using this description of the Hamiltonian. We need to have uniqueness. That is, we need to have a particular external potential has to correspond to a particular ground state density. And you can reason this out fairly simply. If you had two external potentials, and when I say that, you can also think of it as two separate molecular systems. So if I had two external potentials that led to the same density, then given that density, we wouldn't know which system the density corresponded to. So if that were the case, this kind of line of thinking would be useless. Another way to reason this out is just, if this were true, then if we had an energy functional, we'd get the same energy for two systems, which wouldn't make sense. So this example is just like a benzene with different carbon-carbon bond lengths, right? And so those two systems are clearly going to have different energies. So uniqueness must be proven for the rho, or the density, to be used in a quantum mechanics calculation.
So Alan, if we go back to slide 5, like the Born-Oppenheimer Hamiltonian, is that using any is that looking at like the exchange or the correlation or anything associated with that? It looks like you're just defining everything classically of just charges repelling each other and attracting each other.
Yes, well, the hard part about, so one, exchange and correlation are in this Hamiltonian. They appear in this two-electron operator. I mean, if you, the correlation comes into effect when you actually integrate over the operator, because then you have to take into, so like this is like, the way it's presented, you kind of think about it as an electron here and an electron here, and they feel each other. But remember that electrons are like not actually in a discrete place in quantum mechanics. So you have to integrate over it being everywhere and this one also being everywhere. This is where the difficulty comes into in QM. It's all in this term. It's not. It's a two electron operator, so it includes the exchange and correlation effects in there.
So even though it looks like this is being evaluated completely classically, it's not.
Well, so classic would be a one electron operator. It's like Hartree-Fock. You would have the operator would be an electron moving around in a density field generated by all the other electrons in the system, instead of the explicit particle-particle interaction that we have here. Yeah.
Okay, thank you.
Any other questions? At the end of the outline, whenever I put up an outline slide, that's probably a good point to ask questions if you have any. Yeah, so we've motivated density as being.
What have we not figured out about uniqueness yet? Because we've already shown that we can figure out the number of electrons and the locations and the charges of all the nuclei.
Well, you could imagine a density that just has like a slightly higher density here. And then based on what I've said, that density would give you the same external potential as what I have up there. Right?
Is that a problem?
Based on this reasoning, yeah. Like if it's possible to have two dense, I mean,
There would be two different densities leading to the same
system.
external as opposed to two externals leading to the same density.
Yeah, so the uniqueness point so I basically, on this slide, I showed that the shape and the cusp part of the density is very important. The uniqueness point kind of indicates that everything away from the cusp is also important, has to be unique.
So do you need uniqueness the other way then?
Yeah, it's a bijective. It's like one-to-one both ways.
Okay.
Yeah. All right, so we're all convinced that densities can be used in quantum mechanics calculations, besides the fact that everyone uses them nowadays?
Well, you haven't convinced us of that yet. You told us a big problem.
I've almost convinced you. Good call, Robo. All right, so next we're going to go through the Hohenberg-Kohn theorems, which basically prove uniqueness. So HK1, there are two parts, or there are two theorems. HK1 just says that the external potential is uniquely determined by the ground state density. There's a one-to-one correspondence between the two. The proof is fairly simple, but put in words, you can basically just assume that two external potentials lead to the same density, and you get a false statement where an energy is less than itself. Therefore, the assumption is false. This theorem is also called the existence theorem because since it proves uniqueness, it kind of proves that the density is useful and that an E energy as a functional of density exists. All right, yeah. So I just said that, so HK1 basically tells us that this E of rho exists. And so in density functional theory, we talk about the universal functional, the E of rho that can be applied to any system. But in particular, in density functional theory, we're only interested in these two terms as being universal, right? Because the external potential depends on the system you're looking at. So if you see the terms in like some density DFT related text, universal functional, they're really referring to the energy functional for the kinetic energy and the electron-electron repulsion, not including the external potential. Okay, and that's normally called F, from what I've seen. All right, that's part one. It it tells us that an E of rho exists. And then part two is basically consider rho prime different from the ground state rho, the true ground state rho. Then, given the energy functional, the energy of rho prime is greater than the ground state density. This basically just gives us a criterion for distinguishing the ground state density. All right, and then I just want to briefly point out, this is kind of a detail-oriented detail. But basically, so this asterisk just means, to be rigorous, I mean different in the sense that the densities still integrate to the same number of electrons, so they're part of the same n representable set. But they're different within the set. So of course, if this was different, if rho prime was part of a different n representable set, its energy could be lower than the ground state rho. So in density functional theory, you'll sometimes see the term n representable, and that means that the density integrates to whatever n you're interested in. Okay, so HK1 and 2 are actually really great. They tell us that density can be useful, and they tell us that it's possible to distinguish the ground state density from all others just through the energy of it. So practically speaking, they leave out a few crucial details. HK1 doesn't tell us the form of the universal functional. Without the actual equation, pretty useless. And HK2 doesn't tell us how to search for the ground state density. As I mentioned earlier, we are restricted a bit. Our search space is a little smaller because we're looking only in the same n representable set. But within that n representable set, it's not really practical to just compare each and every density to each other, right? So it's not the best strategy. Okay. All right, and I just wanted to point out a few things about the universal functional. This basically relates to Robo's question. Some of you may be familiar with various quantum mechanical concepts. The ones I'm most familiar with are exchange and correlation. They're actually all included in the electron-electron repulsion term. But it turns out that kinetic energy is also difficult for reasons that I'm not intimately familiar with. So both terms have difficulties in finding the universal functional, is the point of this slide. So people had some early approximations to the universal functional. The first one was just taking an extremely simple system, the uniform electron gas, that has constant density over the space. And you can see that you can write out a universal functional for it. And for particles, you can also write out the kinetic energy functional part of the functional. Again, the form of these equations is not important. I just want to emphasize that they are dependent solely on the density. So, they kind of are fulfilling the promise of DFT for useless systems. But no, they're probably pretty useful. Yeah, so the problem is that we don't have a universal, one problem is they're not accurate enough for application to molecules. The second problem is the true universal functional is still unknown today. Yeah. So then the question becomes, what systems can we get functionals for? How can we, mess with DFT such that it gives us a practical method? So all the difficulty, or a lot of the difficulty, comes from the interactions of electrons with one another. And so a simple strategy to approach this is just to move to a non-interacting system in which a lot of these troublesome interactive terms they don't go away, but we can get a large portion of the energy without considering them. So in a non-interacting system, all of our functionals will be one electron terms, and they're known for the non-interacting kinetic energy and non-interacting electron-electron repulsion. And so that's exactly what Kohn-Sham did, which we'll talk about next. And Eric, this is why orbitals even exist in DFT. Because up to now, we've been just talking about densities. No real reason to have them. So, do we have any questions? Yeah.
Could you explain the HK2 again? That slide.
Explain how? Like, it basically just says that.
Part of that theorem. I didn't exactly understand that theorem.
Okay. Okay.
Yeah, this one. Like, what is the rho prime? Some arbitrary.
It just means a different rho.
Okay.
Like some rho different from the ground state density. It basically just says the ground state density will have the lowest energy out of all the other rhos that you could consider. I just think of this as like giving you a criterion for distinguishing the ground state density. Was that okay? Clarification enough. Okay. So in Kohn-Sham, we do exactly what we just talked about. So he starts with the assumption that you can have a fictitious system of non-interacting electrons that move under the influence of a Kohn-Sham potential. And this system will give you the exact same density as the real system that has interacting electrons that moves under a different potential, the real potential. So the blue is just density in this picture. And this kind of makes sense. If you turn off interaction between the particles, of course they'll move around differently. But if you make them move under a different potential field, you could mess with the field such that it mimics the exact same effects that you get from interaction. So all the effects of interaction on the density, electron-electron interaction, are wrapped up in this Kohn-Sham potential. And now the problem becomes determining what exactly this Kohn-Sham potential is. Okay? So here I've just made it explicit, the splitting of the Hamiltonian into the non-interacting and Kohn-Sham potentials. Here we just have, so we're just starting, these two lines are just starting with the Born-Oppenheimer Hamiltonian that I showed you earlier. So if you treat each of these two terms as non-interacting, you'll get the non-interacting operators, as well as the corrections, which we're not, they're just corrections. We don't have an explicit form for them. So we have non-interacting plus the correction due to interaction, and non-interacting plus the correction due to interaction. And we bundle those two corrections up into this exchange correlation potential. And so the Kohn-Sham potential is just these three terms put together. Okay? So the important part about this is just that all of the differences between the non-interacting and interacting Hamiltonians is contained in this exchange correlation potential. Another way to think about it is that these two effects, many body effects, have been removed from EE and stuck in XC. For those of you who are familiar with perturbation theory, this is kind of reminiscent of that, just because you're taking your Hamiltonian and you're separating it into a system that you know a lot of analytical things about, and this unknown part that you're hoping is really small, and that you can, in perturbation theory, you hope it's small and that you can approximate it. Here, you hope it's small and that you can find a useful approximation to it. Okay. Oh, right. Once you make this non-interacting, in the DFT literature, it's also called like Coulomb classical Hartree electron repulsion. I'll probably be calling it Coulomb or classical throughout the talk. This is the other slide, just made more explicit in case you don't follow talking as easily as you do text. Again, I just want you to notice that the exchange correlation energy is composed of many different corrections. And I want you to notice that we know these three explicitly. We have, the expressions for these. This is the only problem in cone-sham DFT theory. The only unknown, I should say. So now we're going to talk a little bit about why cone-sham uses orbitals. So basically, once you move to a non-interacting system, your Hamiltonian is composed completely of one-electron operators. And this simplifies the problem of finding the wave function actually a decent amount. Your wave function for a Hamiltonian of one-electron operators is a single Slater determinant. So that's good. And this single Slater determinant is solely composed of one-electron basis functions, which all of you know as molecular orbitals. All right? And we know how to solve for molecular orbitals from wave function theory, specifically Hartree-Fock. We basically run the exact same procedure as in Hartree-Fock. We just use, instead of a Fock operator, a cone-sham one-electron operator. The details don't matter. They're both one-electron operators, so you can solve for the orbitals using a self-consistent procedure. That's why if you run QM calculations and you compare Hartree-Fock and DFT, they actually look really similar in terms of the output. It's just setup stuff and then an iterative procedure and then your energy, right? They both undergo a SCF procedure. Oh, and that's just a schematic of the SCF. You input a guess density, you minimize the energy with the orbitals, check for convergence. If not, you generate the new density from the new orbitals you just solve for, and you iterate. Right, so this I just also wanted to point out, as chemists, we're often used to really using orbitals to kind of interpret our systems and what they're doing. I just wanted to point out that in cone-sham, the orbitals really rigorously don't carry much physical significance. They're literally just the orbitals solved for, such that the Slater determinant that we construct from them gives you the exact ground state density. Exact, assuming your exchange correlation potential is known, which it isn't. But yeah. And so, if you read about like what do cone-sham orbitals and eigenvalues mean, you'll often run into a line that says something like this. They often are said to have no physical significance. However, there has been one theorem that I found. Janak's theorem basically states that the HOMO eigenvalue, at least, should correspond to the to the ionization potential. That's Koopmans for Hartree-Fock. It's different. But yes, Janak is the Koopmans analog in DFT. But yeah. Yep. But I will then. I'll also say that people still use cone-sham orbitals and eigenvalues. They often interpret them with physical significance in the literature, and empirically they do seem to match up. It's just that there's no real reason to believe that they should match up. They just happen to. No rigorous reason. There probably is a reason. All right, so this was like kind of a long portion. So the takeaways were, in cone-sham, we move to a non-interacting system. Therefore, we allow a large portion of the energy functional to be known and therefore evaluated, given a density and an energy functional. we put all the unknowns into this exchange correlation term, which is the unknown. And Kohn-Sham also introduces orbitals into DFT because we've moved to a 1-electron Hamiltonian. All right, and these are just some bullet points. So Kohn-Sham DFT is formally exact and variational. Right? If we knew this, we would know the energy. We would know everything we would want. However, because we don't know the exchange correlation, we input approximations to it, and then in that case, Kohn-Sham DFT is like formally not exact anymore. But in the literature, typically you'll find that DFT is talked about as being a variational method. I just wanted to point out that technically it's not. Technically. Okay, questions? Alonzo.
So, for the exchange correlation energy potential, you said that also includes the self-interaction energy. What does the self-interaction energy represent?
That's just that arises from treating it as a 1 electron. Though, where did I put it? Here? Yeah. So the easiest way to so the 1 electron form of classical Coulomb repulsion, you basically just have an electron moving around, and it experiences the density of the other electrons, right? So you put like 20 of your electrons in their respective orbitals, and they generate a density. And you have your 21st electron, and it's moving around, and it feels the density of the other 20. If you're familiar with Hartree-Fock, this is a similar concept as in there. So the self-interaction error, as the name implies, is the electron interacting with itself. And this can be, you can think about this, if you think about a 1-electron system, this term will have a finite value because the electron will be moving around in a field that's generated by itself. So it will be interacting with its own average density. So that's the self-interaction error. In Hartree-Fock, that's canceled by the exact exchange expression. But we don't have that here. All right? So self-interaction arises from treating electron-electron repulsion in a 1 electron, with a 1 electron operator, or in a classical sense. Okay? Okay.
Can you go up a slide 1 second?
Back or up? The other way. This way. Just tell me when.
Wait.
Okay, the other way, because we went too far.
Right there. Oh, sorry. 1 slide forward.
Mm.
Why is V not interacting incorporated in a Kohn-Sham?
Why is
Why is the 3rd line going to the 4th line? Why is N?
Oh, I'm just saying VKS is just all 3 of these added up
In the
together.
next slide, you said that we know Ni and TNI, but we don't know those last 2 terms.
Which? Sorry.
So we
that,
know
we don't know that one. We don't. Okay, so VKS is just these 3 terms put together. So we don't know the entirety of VKS because we don't know this one term.
Yeah. So
where
does ENI come from? Energy of non-interacting come from? I thought that came from VNI. So where does energy non-interacting come from? The second term and the
this,
yeah.
this,
Wait. So
this.
what you just said that VN. So where does EX exchange come from?
This is probably better talked about over here. Just know so Hamiltonian, like H equals and E equals are the same thing.
Yeah.
Okay, yeah, so you're, okay. So here we're still at an interacting system, like, what DFT was originally formulated in which we could not find universal functionals for. In this line, we make all the operators that we can, non-interacting, but to keep the Hamiltonian exact, we add in correction terms. So these deltas. All right, so this went here. This split into a non-interacting term and a correction term. This split into a non-interacting term and a correction term. And that stays the same. So VXC just bundles these two together. It takes the two unknowns and we put them into a single term. Did that?
Yeah, yeah.
I wasn't.
I think it was just the next slide that was that's going from the first to the second equation on the next slide was a little confusing to me. So.
Does it follow now?
Yeah, yeah. I understand what you're saying. I just don't know exactly where the terms went. Like I understand the concept.
Okay, well, all the terms are in here. All the unknown terms are in there.
Okay.
And the unknown terms just come from splitting the interacting system into known and unknown.
Okay.
Right. Yeah. Okay. Other questions? Josh?
So is it effectively that solving the DFT is doing Hartree-Fock, but on the Cone-Sham potential instead of the Hartree-Fock potential? Is that essentially the only
Yeah,
main difference?
that's a good way to put it. Which is why they look
So
so
it's like
similar.
instead of doing the correlation, we're just going to do Hartree-Fock on some artificial potential that we hope gives the answer that corresponds to.
Yeah,
Okay.
and it does if we had VXC.
Yeah.
Yeah. Okay. Okay, cool. So we've gone through all the theory stuff. So really, I feel like understanding this stuff is important so you can understand, if you ever are going to go read a paper about why a functional is developed a certain way, having some familiarity with the terms up here will probably help you understand the paper. And that's why I tried to, like, this was the bulk of the presentation. Okay, so now we're going to talk about functionals, different ways of making them, and their hierarchy within DFT. So, EXC is the only part we don't know in cone-sham density functional theory. So we split, and so we want to find approximations to it. In the literature, they split it up arbitrarily, I might add, into two distinct components, the exchange functional and the correlation functional. And in creating these, they take different amounts of information from the density. And the amount of information that you take determines where you are on this Jacob's ladder thing. This is basically kind of like in basis sets, you have minimal, double, triple, etc. And the higher up you go, the more accurate you are. It's a similar idea here. You start at the bottom with only local information, then you move to semi-local, then you add in some exact exchange. So as you go higher up the ladder, you should be more accurate. Yeah, and naming schemes concatenate the names of exchange functionals and correlation functionals. So the bottom rung is the local density approximation. These are functionals that depend purely on rho, the value of rho at a specific position. So they're called local functionals. They're based on the uniform electron gas, for which we have an exact exchange functional. We don't have an exact correlation functional. And this is actually just parameterized from highly accurate calculations where we get like a really good energy, we extract out everything else, and then we fit a function to the density, or to the density such that it gives you the energy you've got left over. So this is one of them. You can see it's actually quite complicated. So you can imagine that there are probably no analytical integrals for this. And this is kind of an aside for anyone who's run DFT. This is the reason that DFT uses grid sizes. The grid is basically referring to how we numerically evaluate the integrals that are going to be required here and here. Right? Since there are no analytical ones, we've got to do them numerically, and so we use a grid. So if you've ever read the manual of your package, your QM package, it probably has mentioned something about like standard quadrature grids or whatever. But that's why grids exist in DFT. The next rung up, if we're going to use the value at a certain point, why don't we also include the slope? So we add in the gradient. These are semi-local functionals. They're often either built as corrections to a local density approximation functional, or they can just get rid of the LDA term entirely. All right. So this will come into play later when we talk about B3-lip. So these are some examples which you may or may not have heard of. So B-lip is a fully defined GGA, external or exchange correlation functional. So we can keep going. Meta GGA just adds the second derivative, as well as the kinetic energy density, semi-local, some examples. I guess, Okay, so now we're on to hybrid functionals. I'm going to spend a little more time here, just because this is the class in which you find B3-lip that is used widely in DFT, and it's basically just like a go-to choice nowadays. It adds a percentage of exact exchange to your exchange correlation functional. And that shows just a neat little statistic I found. All right, so an easy way to motivate hybrid functionals is that the exchange the exchange arises from the antisymmetry, right, of our wave function, which is just a property resulting from electrons being fermions. So exchange is a non-local effect since it pervades throughout the entire wave function. So then the reasoning goes, how can a local or semi-local functional truly approximate this value accurately? So we include, so the answer to this question is it can't. So we explicitly calculate the exchange, which we know how to do from Hartree-Fock. And so your functional now becomes, has a bunch of parameters that include specific fractions of exchange from different sources. So B-lip was a GGA functional, right? So so that's why in the equation, the B3-lip equation, it has LDA in it, right? So just remember, GGAs are sometimes added on as corrections. So in B3-lip, we have the LDA exchange, the GGA exchange correction, and then we have the Hartree-Fock percent or amount, which is controlled by this A parameter. And then for the correlation section, we have, again, the LDA part and the GGA part, or LYP. And this C parameter was added in just for more flexibility when they were parameterizing B3-lip. And then you can take hybrid functionals even further with range-separated hybrid functionals, in which your amount of Hartree-Fock exact exchange changes with the type of your interaction, short versus long range. Because at short range, semi-local information is probably good enough. At long range, you need the exact exchange. All right, and that's as far as I got. You can also, so if that motivation back there was like unsatisfying, you can more rigorously motivate it through this adiabatic connection that's found in density functional theory. I didn't really get around to really presenting that in a simple to understand way, so I just axed it. But this paper explains it really well. If you want to read like 6 paragraphs, it's quite intuitive, I think. So there are more corrections you can add to functionals, dispersion corrections. There are other types, double hybrid functionals, and nowadays they're even trying to, because the exchange correlation functional is so complicated, they're trying to use machine learning to find the best one. Oh yeah, and as far as practical recommendations for functionals, I don't run DFT calculations on a day-to-day basis, so I don't really have a good answer for that. What I do know is that B3-lip is a good first choice, and like unless there's a really particular reason that you need, for instance, dispersion corrections, no one's really going to argue with you on that for like an initial investigation, at least. Otherwise, I'll quote every manual that I've read. It's read the literature. Because DFT, like these functionals are all parameterized off of test sets, all right? So if your molecule falls within one of those test sets and the paper shows that this functional does well for that test set, then you might as well use that functional. But really that's like the only way to really rationalize the use of a particular functional to a particular system, just based on past comparisons. All right, I want to thank Alexei and Alexander from the Zagid group, who are much better at DFT than me. They're really helpful, and they explain things well. So without them, this would probably be a bit harder for you to understand, or a lot. Mina and Cody for organizing the workshop and forcing me to learn some DFT. And then these are some sources. A lot of my sources were actually from like online, but these are like books that you can find, and I have a few recommendations on them. This book in particular, very simple to read. If you want like very general knowledge of DFT and the equations and everything, you can read this book. It'll take you like 20 minutes, and that's all you'll get out of it. It glosses over a lot of the details. And then so I also read Cody's book. It's basically in the middle. It has some equations, but it also explains things pretty nicely. And finally, if you really want to dig into it, you can go to this guy's website, Kieran Burke, out in California somewhere. So that's where the title of the talk came from. This is the first source I found. It is much more rigorous than these other two. It has many equations, many exercises to work along with. So it is, if you want a fundamental understanding of DFT beyond, yeah.
I was just going to say, I have actually been, I needed an introduction myself for something recently, and Walter Cohn has a 1998 Nobel lecture that I found pretty helpful.
Okay, yeah. There is that one too. But yeah, that's where you can find that, and you can find the Nobel lecture on the internet, I'm sure. Do we have any further questions? Alonzo?
Yes. Could you comment on what effect does different grids in Q can have with respect of evaluating the numerical integrals?
No. Well, I mean, like the obvious is just that the tighter the grid, the longer the calculation, but the more accurate. As far as like what is a good grid size, I assume the developers chose that with much more experience than I have. Like I said, I don't run DFT. I've just noticed that sometimes when you run it, I don't run it every day. I've noticed sometimes that when I run it, the program will print out a warning like, oh, you might want to up the grid size or tighten the grid. And I didn't really know what that meant until now, but it's obvious. It's just because we don't have analytical forms for these parameterized functions that are like 20 terms long. So I have no recommendations for grid size, but all the programs come with standard or default settings.
So the grid is solely because of this physical?
Yeah, I mean, it's a numerical integration of an expression. So you need to define at what points you evaluate the expression, and then you take the area under it, blah, blah, blah. Yeah.
I think like the QChem manual has suggestions for grid size for particular system sizes.
Okay. Yeah. Yeah. First stop for any questions in your DFT calculations is to look at the control options in your quantum mechanical packages. And then you can go ask people from the Zagid group. Or yeah, someone else. All right, I hope that was a fairly useful introduction to the background of DFT. And you can always ask me more questions later. I'll be happy to look into them. Maybe. Bring me cookies. Mm.